All right, so this will be a short explanation on the notes that we have between mass and the mole relationships. So a term that we've used is AMU, and that's the atomic mass unit. And that's just the mass of a single proton or neutron. It would be 1 AMU. And carbon kind of sets our reference point here. So the isotope of carbon-12, and that would be 6 protons, 6 neutrons, so a mass of 12 AMUs. And so if we have a mole's worth of carbon-12, we would have 12 grams. So how that works is that Avogadro's number, or 6.02 times 10 to the 23, is the number of atoms of carbon it takes to have a mass of 12 grams. So this sets up a nice relationship using the atomic weights on the periodic table. So if you have a single atom of carbon, it would be 12 AMUs, or the average atomic weights based on their isotope abundance. And if you have a mole's worth, then that would be the molar mass, and it would just be the same number but labeled with grams. So I have posted also, besides using your periodic table, this list here. It's a nice handy reference sheet. It has all the elements in alphabetical order and their molar masses in grams. So I'd recommend either printing that off or just having it open in another tab when you're working with it. If you do want a paper copy but can't print it off at home, just let me know and I can leave a stack on a table in the hallway outside of the office for pickup. So anyways, let's talk about how we can go between mass in grams and numbers of moles. So we know that the atomic mass is the molar mass in grams, and that's grams per mole. And we're going to be using everything to 100th place. Some places on your periodic table you might have to 1,000th or more. We're just going to round off to the 100th for all of ours. So when you look at your periodic table or the chart, for example, copper has an average atomic mass of 63.55 AMUs. And then if you have a mole's worth of copper atoms, you would have 63.55 grams. So right here, this is right around 63.55 grams of copper. So that is a mole's worth of copper. And it's an amount that you can hold in your hand, which is an impressive thing to consider, considering that an Avogadro's number, 6.02 times 10 to the 3, is an enormously large number. But because atoms are so small, that's how it works, is that we end up with just a small amount that you can hold with a mole's worth. So likewise, all the other elements listed there are just the atomic weights, and that would be the AMUs per atom or grams per mole. One thing to keep in mind is the diatomic elements. For example, if you have a mole's worth of hydrogen gas, well, what you have is a mole's worth of hydrogen 2 molecules. So you would have to double the mass for each of these things. So all of these, for example, nitrogen has an atomic mass of 14.01 or 14.01 grams per mole for nitrogen atoms, but because it's N2, you would have to double it. All right, then what we're going to be looking at is at molecules and formula units and finding the molar masses of those. So for example here, water is made up of 2 hydrogens, 1 oxygen. So all you do is take the mass of a hydrogen atom and double it, because there's 2 hydrogens. And then oxygen is 16.00 grams per mole, and there's only 1. So then you would just add those up and you get the total molar mass of a water molecule. Similarly with nitrogen dioxide, NO2, so 1 nitrogen, 2 oxygens, total of 46.01 grams per mole. And this is where your nomenclature is going to be important. You have to remember how to write formulas given names. So calcium sulfide, so 1 calcium, 1 sulfur. Aluminum carbonate, you should know that aluminum forms a 3+ cation. Carbonate is a 2 negative, so a common denominator of 6. So it's going to be Al2CO3 3, which means you can have 2 aluminums, 3 carbons, and 9 oxygen to add up to 233.99. And you should be able to see how to do the rest of these. You'll notice that the masses for these are going to be larger because we're adding all these different pieces together to get larger molar masses.